I'm delighted to be here. Thank you very much for organizing this and sharing this. And so in the interest of full disclosure, I'm not Chris Brown, the rapper. That's a different Chris Brown. I suppose if people thought this was going to be the rapper, this would be full. But this is just going to be about axiomatic design and the interesting times I've had with it. I had the great privilege to have met Nam Su in about 1980 and sort of opened my eyes to design is not about drawing or drafting, but design is about developing concepts. And so I'm really pleased to be here to tell you about the axiomatic design or introducing axiomatic design. And for those of you that have seen this, have seen me introduce axiomatic design before, there are some new things. So I get to teach this quite a bit at WPI. There's somehow we ended up with a goat for a mascot. And our motto is in German, Lehre und Kunst, that we come from in 1865. So axiomatic design originates with Nam Su, who back sometime in the 70s got a grant from U.S. National Science Foundation to start looking at design to see if there were axioms, laws, something that covers design like mechanics. And the premise is that good design would be based on self-consistent axioms that would give us the best solution for all design problems. This is quite a radical thing. A lot of people think that design should, no, this is creative and you can't limit it. You can't have rules for design. No, this is design. This is not a knife fight. We can have some rules. For those of you who don't. But anyway, so design, art, philosophy, science. So art is marvelous, wonderful, beautiful. I love it. But and it is involved in design, and we can put it in systematically, although I won't talk about that today. But there's an interesting progression as we go from philosophy, like natural philosophy, which sort of governed all science until like Newton or something. And it's what we call thought before it solidifies into a scientific discipline. So, and what makes a scientific discipline? A few simple, self-consistent laws that we can apply to a wide variety of problems. So I put Sue up here with this Galileo, Newton, and Einstein, because I think that this is what we're looking at, and we can ask the question, I suppose, as I'll ask in a moment, about how we're doing design. So looking for things like law of gravitation requires looking at commonalities across very diverse applications, just like an apple falling on Earth and the little lights moving around the sky at night that wander around that the Greeks called planets. And so what are the commonalities between a water faucet and an online electric vehicle? And how are those things connected? Well, two axioms. Now, oftentimes we get sort of engrossed in the application, how to apply axiomatic design, but it's called axiomatic design because we've got two axioms. And so we need to get these out in front, all right? So we have the independence and the information axiom. There's corollaries and theorems. I'll leave that to you. So we have the design theory, and then we have a design method that's based on that. Now, when I talk to like our engineering students presenting their senior projects, so after 4 years of studying in the United States, investing over $250,000 now, 4 years of your life, and it's design that sort of distinguishes engineers from scientists and things, creating something new. And it says, so what design method did you use for your project? And they sort of look at me, oh, the usual or something. And it says, and what design theory is it based on? And they look at me like I came from Mars, like they'd never heard these two words juxtaposed before. And alarmingly, when I go to GE aircraft engines and teach a course on axiomatic design, as I've done, I get the same response. Like, what is the difference between the design method and theory that you're using now to design aircraft engines and what you did in high school before you went to college? Not analysis. Yes, that has developed a lot, but the design, the way you come up and develop a concept, ideas. and they can't think of anything. I try not to think of that when I'm flying in airplanes, as I was doing the last couple of days. But so this is a rather sad state, but it's difficult because engineers like to think they can do design better than any other engineer. And I don't need a method, I do design. So, all right, axioms. So what do we want in design? So we want a design that is adjustable and controllable. Just because I haven't moved yet doesn't mean I'm not going to, but thank you for making the adjustment. All right, good, okay. So adjustability and control. We like to avoid unintended consequences. These are often what lead to cost overruns and delays in design. We finally get to make a prototype, start testing out, geez, this doesn't work. Modularity is great because we can switch things out, like the Toyota production system and Toyota design system. And so this, if we require this independence, we eliminate some candidate solutions. And I'll talk more about how we do that stuff. So that was axiom 1, maintain independence of the functional requirements. And then minimize the information content. Now this gets confusing because some people think, well, information, isn't knowing more good? I like more information. Not if you need that information to make a design solution work. The more instructions that it requires to get something to work, the greater the chances that somebody forgets one, doesn't understand one, misapplies one. And so that reduces the probability of success. So when you see information content, you can think sort of 1 over the probability of success, as it is quantitatively there. Information content is equal to 1 over the probability of success. And for the people that are familiar with Shannon's information theory or Boltzmann, for entropy, it's similar. So as I said, more instructions. So information content does not equal knowledge. We have to separate these two things, at least when we're considering this. So axiom 2, it essentially encompasses axiom 1. What are we looking for? Probability of success and having our design work. And anyway, because axiom 1 was about independence, lack of ability to control and adjust is going to affect our probability of success. So we could also say axiom 2 will reduce uncertainty and complexity in design, so minimizing malfunction possibilities and influence of wear, temperature, other things that change people. Robust design. So modular design, robust design, those are things that people often talk about, but putting those systematically into a way of developing your design solution. So axiom 1 eliminated some solutions that that are not independent, and axiom 2 allows me to rank the remaining in terms of probability of success so that I can pick the solution that has the greatest probability of success. So speaking of adjustable designs, here we are adjusting another one. Okay, so most people, although they may not be able to articulate it, use an algorithmic sort of approach to design. And it is appropriately lauded in these circle diagrams because it is actually designed to send you going around in circles. The idea is algorithmic, good process, good result. It requires iteration, trial and error. It's missing the evaluation criteria, except for when I get to doing the prototype and testing the prototype, did it work or not? And then we'll modify it and we'll do some more research and we'll try it again and have some brainstorming. Yeah, terrific, okay. But there's no way of selecting the best solution a priori until you try it. And then you don't know if you have the best one. You go, oh, geez, we got a prototype that works. So axiomatic design, we've got 2 axioms, and this essentially guarantees the best solution for a set of functional requirements. So we'll be talking about the importance of getting a good set of functional requirements. It also has an overarching and inclusive structure. So yeah, we could have little bits of algorithmic stuff in there if we wanted, and I'll talk about how I like to integrate something called CK theory. So, and we need a process for applying Sue's axioms to make this work. We talk a lot about design thinking, and we have to do design thinking. So when you ask people, go, oh, we have to do design thinking. And you go, so what is design thinking? The answer I get most often is, oh, thinking about design. And you go, okay. Do you have another one without just switching the order of the words? So being an American, I like to go back to the architect, Louis Sullivan. Form follows function. In other words, function has to come first for form to follow it. So form here, so that's functionalism, which is a major part of sort of evolution of design. So this comes to us actually from the late 1800s, early 1900s. And so you can see an example here in Chicago. So think of a function. So this is what Nam Su says, so axiomatic design. Get a function that satisfies a customer need, or develop a function, formulate a function that satisfies a customer need, and then select the form, the physical solution, the design parameter. So remember these abbreviations: FR, functional requirement, CN, customer need, and then DP, design parameter. And the design parameter is the physical solution. So we have to watch out when we're talking about it, because design can be a result, can be a process. So lots of times we'll talk about the design solution being the physical manifestation of how we're going to do it. So there's this neat example that I credit Professor Selenius with, and as I understood it, although maybe some other people know more about this than I do, he got first introduced to axiomatic design and decided to spend a year at MIT learning more about it from Nam Su, and he came up with this example then. And there were several of us when Nam's book first came out in 1990, and friends from Portugal who decided once they first saw that book, I've got nothing more important to do than understand this. And some of us literally stopped everything and said, I've got to understand this book. I had to read it 3 times. In order to teach from it. But anyway, let's get to this example. So axiom 1, independence. Is this a good design? So before you can decide if it's a good design or not, you have to say, well, what is it supposed to do? Who is it trying to satisfy? And so let's just talk about the customer is the person who wants to wash their hands and wants to control the water, be able to adjust the water. And so we want to adjust the amount and the temperature, right? Flow rate and the temperature. And so what do we have for adjustment in this kind of setup? Cold water valve, hot water valve adjustment. Right? So we got 2 handles. So is this a good design? So the question is, can we adjust flow rate and temperature independently? So functional requirement 1, adjust the temperature. Functional requirement 2, adjust the flow rate. And the design parameters we have: control a hot water valve and a cold water valve. So if we make a little matrix like this, we'll be using these. We put the functional requirements down the left side and the design parameters across the top. And then we put an X in the matrix if there's an influence. We can get more sophisticated and put equations in. But for right now, we're just going to say, if I write the differential equation relating FR and DP, is there a non-zero exponent for FR1? And you go, yeah, that's right. If I change the cold water, it's going to change the temperature. And if I change the hot water, it's going to change the temperature. As a result, I have an X in these first 2 A1 and A11 and A12 positions in the matrix. And then also, if I want to adjust the flow rate, both of these DPs are going to influence the flow rate. So as a result, and we all have had experience with this at home, we sort of know how to adjust these. If we have the system at home, we go to a new place and then we make a guess, stick our hands under to test our prototype. Like, whoa, geez, and I get too much water, so all right, I got to turn one of the, it's too hot, and then but after a few iterations, non-productive iterations, because I'm not getting my hands washed, that's not very important. I can waste a little water still. We haven't completely ruined the planet. But if this is production, if I'm making computer chips and I have to do these iterations to adjust, what was it, 3 months to make a chip? So this would not be a good system for doing that. So the independence is important. So this is fully coupled. So it's lacking independence. So what's a better solution? So we've all seen these nice sorts of controls for a faucet. So we get up and down that does flow rate, and side to side gives us temperature. And so I can go side to side. It doesn't do anything to the temperature, and I can go up and down, and it just does the flow rate. I'm sorry. Anyway, you can see. So we have the interactions. Side to side gives me the temperature. Up and down does not change the temperature. There we go. Okay. So we have a representation, and this now satisfies axiom 1. It's a diagonal matrix. We could also satisfy axiom 1 with an upper or lower triangular matrix. So that was an example of axiom 1. The example of axiom 2 that I came up with. I wish I had something as clean and neat as the faucet. But in this case, we're trying to make a clamp, and we've got represented here by 2 pieces. It could be adjusting a chair or something like that, and we adjust it, and then we close the clamp, and the clamp is represented here by this oval. And it has in it some sort of spring. I mean, everything's a spring. It could just be a bolt and very stiff, but there's some sort of spring system. And then, so as I close this, my design equation gives me the force. So FR, I want to exert a clamping force. And then my design equation, F equals Kx, where K is the spring constant. And then the physical thing is the displacement as I close the lever. So if I can graph it this way, I can say, all right, well, here's the range of forces that I might have. And if I have too much of a force, I'm going to break something, or I can't close the clamp, and too little force, it'll slip. So there is a functional tolerance in the function, which is applying the force. And then I have a physical tolerance, which is so that what's the dimensions of my cam, and how well have I controlled that? And that, of course, could change in production. That could change with temperature. That could change with wear. So I would like to have a nice big physical tolerance. So if I have a stiff spring, K2, a little bit of motion, I get a nice clamp. And I admit, when I first looked at this problem, I thought, I want a stiff spring in there because I want to be able to exert a bunch of force. But that turns out not to be the best solution by axiom 2. The best solution with a higher probability of success is to allow me more tolerance in dimensioning the cam and getting the spring constant right. So I would like to have a softer spring with a smaller spring constant. That is just a linear system. So axiom 2, lowest stiffness is best. So there's lots of systems that we could design as being linear. And so this allows for variance impacts, as I said. So, okay, so there's the beginning of the introduction. So how do we make this work? So we have, as we said, the root are the axioms. That's why we call it axiomatic design. So how do we apply these axioms? Well, we need some sort of structure. Just like if we're doing Newtonian mechanics, I need a free body diagram. I need something like a free body diagram to apply Sue's axioms. And then I need some sort of process for creating the structure. So I like to think there's 3 parts: the axioms, structures, and the process. So let's take a look at these. So we have 2 kinds, 2 of each. So for the domains, and this is part of the structure now, we have got 4 domains. We've talked about customer needs, and then we generate the functional requirements. So these are what it has to do. These are like engineering terms, what it does. This is sort of, we'll take sort of customers, stakeholders, everybody. And so what sort of things do we want or don't want or something, and we make this stuff, because that is where the value comes from. Then this is what it needs to do, something that I eventually can put in an equation. And this is what it looks like. This is what goes on a print. This is what's often called the design. This is the physical solution. And then I haven't talked much about this, and I won't, but it's the process. That's how it's made. So if I'm designing a design process, I may use all 3 or 4 spaces. And then if it's often, though, I can just use the middle 2. So that's what I'm going to concentrate on, FRs and DPs. And that's what, and that's sufficient, I think, to do this. You can either extend it or figure out how to reformulate design of processes. So you're working with FRs and DPs, but that was subject of the paper a few years ago. So decomposition. So this is another part of the structure, this vertical structure, and I'll show you this more in a moment. But the decomposition is terribly important. And this is, so we talked about functionalism, then we have reductionism. You may not have recognized this, but this is part of our philosophy of science. How can we get down to the most fundamental level of how things work or are built or something? So like we were just looking at, those of us that went to that very interesting tour, we're looking at continuing to try to build chips by evolving 1960s technology. And great, fascinating, I loved it. But then you think, all right, so what is going to be the revolutionary thing that changes this? 3D printing atom by atom, like Richard Feynman talked about back in the 40s and early 50s. But reductionism, how do we break things down to a finer and finer level? And so that's what we're trying to do in the decomposition. So we're looking at these top-down parallel functional physical decompositions. And so we need to decompose to a fundamental level where the solutions become obvious to us. So as we said, we've got the CNs, customer needs, functional requirements, design parameters. We start off at the 0 level and the PVs. So this is sort of domains of scope. So this is the horizontal structure. And then we decompose that. Now I've showed 3 here. We could have lots of different numbers. I like to stop at about 7 or 8 because that's the most that you can sort of do mentally. But you can have systems where you get much higher numbers. So each of these can be subsequently decomposed. I've done it just into 2. A frequent mistake that we see with students, I'll talk about later, is I decomposed it into 1. No, you can't divide things into 1. You have to at least divide them into 2. But so anyway, there's ways of handling that. So the point is that we can keep going. And somehow here at the bottom, it was known before I got involved as the leaf level. The leaves are usually on the top. Okay, it's the leaf level at the bottom, nuts and bolts. But this is where solutions become obvious. So we've got the domains. So this is the horizontal decomposition, and then we've got hierarchy of detail as we break this down for the reductionism. And so we can also look at this with set theory. So one of the things I know in the United States we don't do very well, I don't know how you do here in the Netherlands with this, we don't teach people how to decompose problems. But this is fundamental to problem solving. You get a very big problem, you've got to decompose it. And so what are the laws that we use for decomposing? Well, one is we want the decomposition to be collectively exhaustive. Did we think of everything? So we're starting off at our 0 level up here at the top, the parent, and then we keep repeating this kind of structure. But in a decomposition, we start off with the parent, and then we have some number of children. So if I sum up the children, they have to equal the parent. Now, we'll be talking about this mostly qualitatively, I think. But it has to become quantitative at some point. If I'm designing for Airbus, United States, talk about Boeing, but if I'm designing for Airbus, I hope that they're doing it quantitatively. Because when you come in for a hard landing, I want to make sure that landing gear holds up. The other thing is mutually exclusive. So I want no overlap between the children. So the decomposition needs to be orthogonal. I am creating and decomposing a multidimensional orthogonal space. So usually we run out of dimensions when we get to 3 getting orthogonal. How do I get a 4th dimension right angles to all the other ones? Mathematically, it's easier to formulate, but that's what we're trying to do. So sum of the children should equal the parent, and we can do this in vector notation as well, and that's what we have, these multidimensional vectors. So multidimensional orthogonal systems, thematic decompositions. How do we know that we've thought of everything? So it's nice to have a theme. How do we know that so I got to work with Nam Su on crew survivability systems for the next orbital space plane, which George W. Bush decided to cancel because he was going to Mars, and then he never went. We were waiting. We weren't worried about him getting back again, as Kennedy pointed out. But in any event, we worked for a while on this, and you go, so how do we make sure we keep the crew alive? So a theme was important there. And so as we're trying to do this quantitatively, parents and children are going to need the same units, because otherwise how do I sum them up? So anyway, so here's this idea, sort of a multi-dimensional orthogonal space, and we're thinking about Newton's laws. And so I think we've probably all seen this, I hope, in pre-college physics, adding up the vectors to sum. So multi-dimensional orthogonal spaces. So orthogonal is independent for the independence axiom. So anyway, so we do this. We're developing the vertical hierarchies. So we're looking at detailing the children, or detailing the what we have in the parents as we create the children. So there's children detailing in that particular branch at that level. So branches are like FR1, FR2. We get the first, second, third branch, and then the 1.1 branch could develop on its own. And then we've got the levels as we go down in the branches. Now, I haven't talked about constraints. These are things that design shouldn't do. An important one, because as technology, I guess engineers have done a remarkably impressive job at ruining the climate on the planet. So a constraint should be that design should be sustainable. We should not be teaching engineers anything else. Do sustainable designs. Those are the only acceptable ones. I don't think we're doing a particularly good job of that, but in any event, so anyway, we get the horizontal, vertical hierarchies. We get constraints, which we could put in any domain, and these might be legal, they might be physical. Let's see. Oh, and then there's one other thing here. We got selection criteria and optimization criteria. I'll get back to those in a moment, but those are things that that don't rise to the level of FR. So our process. So we're down to the third thing. We've got the axioms, we've got the structure, and now here's the process. It's zigzagging. Function first, then form. So zig, zag, down to the next level. Decompose the functions. Function first, then form, then down to the next level. So zig, zag, zig, zag. So that's the zigzagging process. At each level, get the FRs first, then go to the design parameters. This is the other word for you. FRs first, then design parameters. Okay, and we keep going down until the solution is obvious. So some decomposition rules. FR should satisfy customer needs. FR satisfy CNs. FR start with verbs. This is something we've got to do. They're stated in the imperative. In the United States, we stopped teaching grammar some time long ago. I have to explain to engineering students what imperative means, but not surprising. So in DPs, this is the form that follows the function. So these are forms. They start with nouns. And we would like the minimum number of FRs, minimum number of pairs, and they have to be collectively exhaustive and mutually exclusive. So lots of people think of design, oh, I'm going to think of things that the other people didn't think of. That's right to a point, but make sure that you're collectively exhaustive and mutually exclusive, because otherwise your decomposition isn't going to work. So C, me, min, collectively exhaustive, mutually exclusive, minimum number. Did I think of everything, and did I avoid overlap and redundancy? So design equations. So the FRs are some function of the DPs, because I changed the DPs to adjust the FRs, get them in the physical tolerance. So I hope you've all had some math and looked at matrices, so I don't have to go into this, but we don't need much. So we're looking at linear algebra. The A matrix has to be square because we want the same number of DPs as FRs. So if I'm satisfying two FRs with one DP, some people think, oh, that's a great design. Look at this. I got only one DP. I'm satisfying two FRs. But now they're coupled and you can't adjust them independently. You might think, do I really need two different FRs there? Do these things have to be adjusted independently? But anyway, so there's different representations we can have for the matrix. And then usually we do it out like this. So visually we can see what's going on more easily. And then what we're looking for is a diagonal matrix where we just have the diagonal terms, but we can also work with a triangular matrix, but we need to be able to get into a triangular form. And so we can do, using linear algebra, we can take things that don't appear to be triangular and readjust them. And so here's an example here. So here is a matrix where it coupled requires iteration to adjust. So this is looking at imaginary complexity. So sometimes we come upon a design that's already done and it's difficult to adjust. Oh, I get this, and now I'm going to change this, just like the hot and cold water. And we go, all right, maybe this is just imaginary complexity, and I can make it, take this and rearrange it so that it becomes upper or lower triangular. And so if you're familiar with linear algebra, you can see that I can rearrange these so that now my order of adjustment is 3, 1, 2. Changing 3 changes FR3, 1, and 2, all of them, but I can fix FR1 with DP1, but then I might do something unwanted to FR2 and take that out of tolerance. And last, I can use DP2 to adjust FR2 and get that within its functional tolerance by changing the physical tolerances. So that's the way I can, anyway, handle imaginary complexity. And there's lots of systems like that you can take a look at. So just overall, the structure can keep on going. It's got some fractal aspects. And so we go from most abstract, increasing detail. The nice thing about this structure is we can integrate lots of other design things in this, and then it can expand so that if I'm talking about designing a new commercial aircraft, it's going to have lots of different components that I've got to get in, the landing gear, the aeronautical, the avionics, everything, passenger systems. And so I can keep on reducing this. If I maintain the independence, I can give the landing gear to some team to design who can give the wheels and the tires and the brakes and different things if they're all modular, and I can understand where the interfaces are. Anyway, so this is reductionism in design. And so while that was a very regular decomposition, it doesn't have to be regular. Some things are more natural and have different numbers of sub-branches and things. So 3 basic steps for axiomatic design. So we want to formulate the functional requirements. We get the CNs somehow. We formulate good functional requirements. Then we devise somehow, select design parameters, or we get a bunch of design parameters. And then we apply Sue's axioms. So we select the best design parameters. And then we have to physically integrate. So once we get through the decomposition, we've got all the pieces on the table. And now we go, all right, how do we put them all together without violating the axioms? Here's a quick example. Local industry is making these pieces for arthroscopy, for surgery, that have to stick into your knee or something someplace. And they required things with very tight tolerances to work together. The part that gets inserted, the ends look like this. They're for nibbling off bits of your meniscus or something. And anyway, it was fed into this centerless grinder by hand. And so I was there sort of teaching axiomatic design at this local company. And the person who was doing it left, and he was doing it very well. They couldn't get anybody else that could do it well. These big wheels spinning around are kind of scary. And the people were dropping it in, and they already had the sharp ends on, and they were worried about those. And every time one got in sideways, the wheels would jam, the wheels would get out of adjustment. And so they're way behind on orders. And they were figuring they would get a robot and just mimic what the people did. Yeah, sounds like a good design solution. But we said, all right, what are the FRs here? Formulate the functional requirements. All right, load the parts. Got it. FR0. DP0, part loader. Okay, why did I have to study axiomatic design to do that for? All right, so let's decompose it. And so what do we need to load the parts? All right, align the parts prior to insertion, maintain the alignment, and protect the operator from the sharp ends. And so we sort of asked the group, does that do it? Yeah, that does it. If we did all that, we'd be happy. I go, all right, so let's see. Some sort of part holder to get that alignment. A V slot, I can slide things along in a V and introduce it. and then a push block, so that I don't have to actually, once I put it in the V slot, as I'm introducing the machine, I don't have to do this. So somebody in the room I could see a light went on. He walked out of the room at that point, and about an hour later, he said, "It's in production, it works." And they were allowing like a month to invest in this. Which robot should we get? How are we going to train it? So anyway, so there's a couple of further decomposition to get to the solution, a V block and a push. But you weren't getting to that unless you decomposed it properly and thought about what are the functions that we actually have to do. So clear statement of functional requirements. So there's another one, especially for those of us that were remember the space shuttles, and as I said, I get to work on this with Nam. So this didn't work particularly well. It was designed supposedly for one loss of crew in 500 missions. How do you design for the one loss of crew in 500 missions? This is quite a complicated thing. What sort of failure is going to occur? What's our probability of success? But it wasn't decomposed. And so we had 2 losses of crew in 135 missions, clearly unacceptable by the original design criteria. So what are the functional requirements? Well, carry people into orbit, carry cargo into orbit, and provide a workspace in orbit. That's what we were trying to do. Now, we put it all in one, partly because it had to make it through Congress, and we needed something, spaceship lands on Earth. And so I think, Congress screws up a lot of stuff. But anyway, so how could we do this independently? So, all right, let's just take a look at Axiom 1 here. Separate launch vehicles dock in orbit. We did this with Gemini. So this was the problem we solved in the early 60s. Right? We could dock up in orbit and hook up. So we didn't need to send everything at once, and we already knew that. And so this orbital space plane, the idea was, let's have something like a Subaru station wagon with wings, and we'll use that. So this is what we needed was, all right, carry people into orbit, a shuttle for personnel, carry cargo into orbit, cargo launch vehicles. This can be much cruder because the cargo can oftentimes stand much greater accelerations, of course, than the people can. We're wimps in terms of how many G's can we handle, and then provide workspace. So we had space stations, still do. So metrics, I want to get into this just because this is something as you develop axiomatic design is important. So if you can't measure it, you can't improve it. Anybody want to contest that? You might improve it, but you won't know if you improved it, I guess. So metrics. So did the FRs satisfy the customers and the stakeholders? What's the influence of the DPs on the FRs? I'd like to do that quantitatively. I'd like to know if this landing gear is going to hold up. What did we achieve collectively exhaustive, mutually exclusive decompositions? And then when I have a design team working on something, how do we tell if we're making progress? Geez, we had our meetings, we did this, geez, we have this, we're supposed to come up with a CAD drawing, but talk to practicing engineers. Yeah, there's guys that come up with the CAD drawings and they're not going to work. They know they're not going to work, but I want to go home. My family's waiting for me. I got to fix dinner or something. So here's my CAD drawing. How can you tell if it works? What are design reviews like? What's this for? What does this do? Anyway, all right, so equations. We've got the decomposition equations and the design equations. And I do the decomposition equation in vector form, and then probabilities of success. So we want to get quantitative. Physical integration we haven't talked about, but it's essentially this V diagram where we decompose on one side, and we get down to all the little nuts and bolts, and then we got to physically integrate these. And so we need to check to make sure we haven't violated the axioms when we physically integrate it. And you can find examples of that. As we represent the design solutions, what do we need to do? So mostly people think, oh, a CAD drawing, that's my representation. But that gives us the problem of what's this for? So the first thing we do in the decomposition is we're writing, essentially. We're trying to verbalize it. And I love this equation. writing is nature's way of letting you know how sloppy your thinking is. And I think we've all experienced this. We think, oh, I got a good idea. And then you try to write it down, you go, I don't know. And then the next level is mathematics is nature's way of letting you know how sloppy your writing is. And then you go, yeah, I can write an equation for this. Not as easy as I thought. All right. So actionability is important. My design representations need to be actionable. I'm an engineer. I don't have to go make this thing. I give it to somebody else. That's why I studied engineering, so I can wear a tie. We're very few of us are wearing ties in the United States anymore. But I noticed that my colleagues had ties on, so I went and got mine out of my room. But I'm an engineer. I don't need to get my hands dirty. I don't need to do real work. Somebody else is going to take care of this for me. So our design solutions have to be actionable, and maybe to another team of engineers. So intent has to be there. FRs, that's the design intent. That's what this part is supposed to do. And it's all right, I can't change it. We've got the plans for Saturn V moon rockets. Hey, they got to the moon before. They only screwed up once, really, sort of. And that we understand what happened. And that crew made it back alive, too. There was enough redundancy, probability of success. But we didn't do that again. We could make another Saturn V moon rocket. We had the plans. We can't change it. We don't know what the design intent was. The people that designed it are gone. This was done in the 60s. And they never recorded the design intent. We got all the blueprints. So we got to do a different one. Anyway. So representation is important. Without representation, you really don't have a design solution. It's not actionable. Lack of intent, we got to know the FRs. Otherwise, we can't make physical changes. So it would also be good from the point of view of, so what were the candidate DPs and why didn't we use them? And so where's the evidence of ethics and sustainability in the design? Anyway, some decomposition rules. So solutions cannot be better than the FRs. All right, so we said verbs, stating imperative, nouns, right? So that's worth looking at again. I guess that's why I have it in twice. Okay, we've gone through that. Here are some common decomposition errors, and this is sort of new. Null comparatives. They aren't actionable. Lots of times we see students writing increase, improve, minimize. Okay, gotcha. That's a good CN because customers want this better. But if I make that sort of part of my design representation, I go, increase compared to what? Okay, intuitively I know, but I can't really design to what is the state you're thinking of improving? And then until when? So null comparatives. That's used a lot in advertising. This razor shaves better. This is a better razor. Better than what? A lawnmower blade, a hatchet? I need a comparative. Wrong verbs. Lots of people start, oh, I want to design a bicycle. You already did. Bicycle is a physical representation. What problem is the bicycle trying to solve? I want a self-powered transportation device. Okay, now we're making progress. And so often students say, well, I want to design a process to do this. You're designing a design process. So that's a good thing. If I want to design bicycles, I'm going to make a company that produces bicycles. I want to design new bicycles. That's an important design problem. But it's not the one usually that the student is thinking of when they say design a bicycle. DP is not completely fulfilling FRs. Children are not summing to the parents. So, oh, it's a key element. I got it. I can figure out how to do it. And then just put the key element down. Your car does not park itself. If you don't plan on time for parking your car, you're going to be late to the show. You got to figure out how you're going to do that. All right. It's not enough just to get there. Okay. FRs. Yeah, FRs containing physical solutions. You want the FRs designed in a solution or formulated in solution neutral environment. I mean, I see students doing, all right, FR, provide a bolt, DP, a bolt. No, why do you need a bolt? So anyway, and single child decompositions, yeah, right? You can't divide something into one. So, right, we got selection criteria, optimization criteria. Not everything needs to be an FR. Make it pretty or something. So, and Kate Thompson, who I'm sorry is here, she is one of the best minds that has worked on this stuff. Anyway, that's a good paper to look at. She presented this 10 years ago at a conference we have from WPI. So make sure you understand what's wanted. Henry Ford supposedly said, if I'd asked people what they wanted, they would have said faster horses. So if he'd listened to the voice of the customer, he would be a horse breeder that we wouldn't know from Detroit. What are the fundamental needs? So asking why. So why do you need a bolt? And you might do that 5 times. This comes to us from sort of the Toyota production system. Get to the root of the problems. Make sure solution neutral. Can you kind of back the FR up towards the customer needs so that you've got a bigger design solution space? I got more room from which I can choose the design parameters. So the more sort of concrete and limited the FR is, the smaller your design space. So one of the things I like in axiomatic design, you can work a lot of other things in. So this comes out of the École des Mines in Paris by this group, Benoit Riels. I think he's from Technion in Israel. But anyway, Pascal Armander from École des Mines. But the idea is we have concepts, but we don't have the knowledge we need. So you get a concept, you go for the knowledge. The concept can generate new things and new knowledge and all kinds of connections. They somehow make a whole book on this. But I love the idea, and I think it's important to integrate that in. Anyway, so suppose we're trying to be creative. FR0 would be innovate, so some sort of axiomatic design for innovation. So develop appropriate CNs, so fundamental development, and so you'd have to decompose all of these things, constitute suitable Cs. Formulate FRs for innovation, create multiple DPs, so some creative methods. So anyway, so here's some steps. Designing a design system. So in this case, the FR was to design of design for innovation. It's sort of like taking an extra derivative mathematically. Okay. So anyway, these stages: conceptualize, branching of knowledge, physical integration. So really to do axiomatic design, those are the 3 sort of stages that you need and the key results that you should be looking for in an axiomatic design sort of exercise. I'm almost done. Hang on, I know I'm the only thing between you guys and lunch. I don't want to get killed. So, all right. So these 3 things and what you get out of it, and this is like a fractal structure, so it can repeat with similar things. Here's something too that I've started to realize: you can't wait until you've completed the decomposition. The space shuttle we had gone through literally thousands of FRDP pairs, getting down to more detailed things just for the crew survivability. So if I'm designing an aircraft, I know somewhere at the beginning, listen, I got wings, I got landing gear, I got avionics, I've got passenger, structures. And so you're going to do upper level decomposition, then some physical integration. Yeah, the wings are going to go on the side of the fuselage, and I keep doing this as I become more and more detailed. Whoops. So that I realize, all right, so I don't just keep going down this way and then go all the way up. I go down, and then, so each of these is projected getting down to lower and lower levels, and each of these is projected at similarly doing physical integration. So I was trying to come up with a new term for this. I thought tacking would be good, because the Dutch like sailing, right? You've got all these fans to get wind. It looks great. They seem to work. When those fans are going around fast, we're getting lots of wind. That's good for the sailing. Anyway, so here we now have 4 books to look at, and we've got one of the editors right here for the 4th book.